every book ever written, every thought ever conceived, every piece of information that has ever existed in the entire history of the universe, all of it will be erased. Not scattered, not transformed, not preserved in some cosmic archive, completely and permanently destroyed. In 1974, Stephen Hawking calculated something so disturbing that he spent the rest of his life trying to prove himself wrong. Black holes don't just trap matter and light, they annihilate information itself. But here's what makes this truly terrifying. Why does destroying information inside a black hole violate the most fundamental law of quantum mechanics? How can the universe permit a process that erases its own history? And if information truly dies in black holes, what does that mean for everything you've ever known, learned, or experienced? This isn't philosophical speculation. This is the information paradox, the crisis that has paralyzed theoretical physics for 50 years. The mathematics are ironclad, the implications are catastrophic, and the solution might be worse than the problem. By the end of this journey, you'll never see reality the same way again. Prepare yourself. We begin. Act 1. The Discovery. The calculation that broke physics. Let's start with what seemed like a simple question. Do black holes last forever? For decades after Einstein published general relativity in 1915, physicists assumed yes, black holes were eternal prisons. Anything that fell in was trapped permanently behind the event horizon. The mathematics seemed clear. The conclusions seemed certain. Then, in 1974, Stephen Hawking was analyzing quantum field theory near black hole event horizons. He discovered something impossible. Black holes aren't perfectly black. They glow with thermal radiation, now called Hawking radiation, emitted through quantum effects at the event horizon. The radiation is incredibly faint. For a solar mass black hole, the temperature is about 60 billionths of a degree above absolute zero. But it's real, and it's relentless. Over immense timescales, 10 to the 67th years for a solar mass black hole, this radiation causes the black hole to evaporate completely. It shrinks, it heats up. Eventually, it explodes in a final burst of energy, and then it's gone. The paradox emerges. Now here's where physics breaks. Imagine you throw a book into a black hole. The book contains information, the arrangement of atoms, the sequence of words, the specific quantum state of every particle. The book crosses the event horizon and disappears from view. Billions of years later, the black hole evaporates through Hawking radiation. Where did the information in the book go? Hawking's calculation showed that the radiation is perfectly thermal. It's just heat with no information content. It's like burning the book and claiming the smoke contains the text. The information is destroyed. But quantum mechanics has an absolute law called unitarity. Information cannot be destroyed, ever. You can scramble it, encode it, transform it beyond recognition, but the information must exist somewhere in some form. If you know the complete quantum state of a system at one time, you can calculate its state at any other time, forward or backward. Information is conserved as strictly as energy. Hawking's calculation said information is destroyed in black holes. Quantum mechanics said information cannot be destroyed. Both couldn't be right. One of the two most successful theories in all of physics had to be fundamentally wrong. The two impossible options. For 20 years, physicists were trapped between two equally unacceptable conclusions. Option 1, quantum mechanics fails. If information is truly destroyed in black holes, then unitarity fails. Quantum mechanics isn't a complete description of reality. This would mean the past doesn't determine the future uniquely. Predictability breaks down. The foundation of all quantum theory crumbles. Every quantum computer, every particle accelerator, every piece of modern technology based on quantum mechanics would be built on a lie. Option 2, general relativity fails. If information escapes from black holes, it must violate general relativity's most fundamental prediction. Nothing can escape from inside the event horizon. This would mean the event horizon isn't a true boundary. Black holes don't work as Einstein described. Space-time doesn't behave as we think. Every test of general relativity, GPS satellites, gravitational waves, Mercury's orbit, would become unexplained coincidences. Both options were catastrophic, but there was a third possibility, even more disturbing. The radical hint. In 1993, Dutch physicist Gerard 't Hooft proposed something that seemed insane. What if the information doesn't fall into the black hole at all? What if, from the perspective of an outside observer, the information never crosses the event horizon? It remains encoded on the horizon's surface forever. Think about what you see when you watch something fall into a black hole. As the object approaches the event horizon, time dilation becomes extreme. Clocks slow down. Motion appears to freeze. From your perspective, the object never quite reaches the horizon. It gets closer and closer, but the final crossing takes infinite time. The object appears to freeze on the surface, its image slowly fading as light becomes infinitely redshifted. 't Hooft suggested, what if that's not just an optical illusion? What if the information really does get stuck on the horizon, encoded in some two-dimensional form? This was the birth of the holographic principle, the idea that three-dimensional reality is actually information encoded on two-dimensional surfaces. But in 1993, this seemed like mathematical philosophy, not physics. Then came the proof. But what if this discovery wasn't the anomaly? What if it was the warning? Act 2. Accumulating evidence. Part A. Observable signatures. Evidence number 1. Black hole entropy. In 1972, Jacob Bekenstein had already discovered something strange about black holes. He calculated that black holes have entropy, a measure of disorder or information content. But unlike normal objects, where entropy depends on volume, black hole entropy is proportional to surface area. Specifically, a black hole's entropy equals 1/4 of its event horizon surface area, measured in Planck units. For a solar mass black hole, that's about 10 to the 77th bits of information. This was already bizarre. Why surface area instead of volume? But it became critical evidence for the holographic principle. If all information about what fell into the black hole is encoded on its surface, then entropy depending on surface area makes perfect sense. The two-dimensional surface is where the information actually lives. Evidence number 2. The thermal nature of Hawking radiation. In the decades following Hawking's 1974 discovery, physicists refined the calculations of black hole radiation. They confirmed that the radiation is perfectly thermal. It has the exact spectrum of black-body radiation at a specific temperature. But here's what disturbed them. Thermal radiation is the most disordered, information-free form of energy possible. It's like static noise, maximum entropy, zero structure. If Hawking radiation is perfectly thermal, then the information about what fell in cannot be encoded in the radiation itself. It must be encoded somewhere else, or destroyed. In 2004, Stephen Hawking publicly conceded that he'd been wrong. Information probably isn't destroyed. But his concession came without a solution. He admitted the paradox was real, but couldn't explain how information escapes.
Evidence number 3, the page curve problem. But this was only the beginning. In 1993, physicist Don Page calculated how the entropy of Hawking radiation should evolve over time if information is conserved. Initially, as the black hole evaporates and radiation escapes, the total entropy should increase. The radiation carries away disorder. But at a specific point, the Page time, about halfway through the black hole's evaporation, the entropy should start decreasing. The late time radiation would need to be correlated with early radiation in a way that encodes the information about what fell in. This creates the Page curve, a graph showing entropy rising, then falling. For decades, nobody could derive this curve from fundamental physics. The mathematics always produced wrong answers. Then, in 2019, researchers using quantum gravity calculations finally derived the Page curve correctly. They proved that information does escape, encoded in subtle quantum correlations between different portions of the Hawking radiation. But the details of how this works revealed something deeply disturbing. Evidence number 4, the Firewall paradox. Then scientists noticed something worse. In 2012, researchers at UC Santa Barbara discovered a new paradox built on top of the old one. If information escapes through quantum correlations in Hawking radiation, then the radiation must be quantum entangled with the black hole's interior. But the radiation is also entangled with radiation that escaped earlier. That's how the information gets reconstructed. Quantum mechanics forbids a particle from being maximally entangled with two different systems simultaneously. The only resolution, the event horizon, isn't smooth, empty space. It's a firewall, a region of such intense energy that anything crossing it is instantly vaporized at the Planck scale. This contradicted general relativity's fundamental prediction. Crossing the event horizon should be smooth and uneventful for a falling observer. The equivalence principle, Einstein's insight that gravity and acceleration are indistinguishable, demands that falling into a black hole feels no different from falling freely in empty space. Until you reach the singularity, you shouldn't notice anything unusual. But the firewall would be immediately lethal at the horizon. General relativity said smooth passage. Quantum mechanics said instant incineration. Evidence number 5, the quantum extremal surface. That's when the pattern appeared. In 2019, research using the ADS-CFT correspondence, the holographic duality we discussed earlier, revealed something extraordinary. They discovered quantum extremal surfaces, special geometric objects that determine how information is encoded in spacetime. These surfaces evolve over time. Early in a black hole's life, the quantum extremal surface is outside the event horizon. Information is on the boundary. But after the Page time, the surface jumps to inside the horizon. This jump corresponds to the moment when information starts escaping from the black hole. The mathematics showed that information doesn't gradually leak out. It remains trapped until a critical moment, then suddenly becomes accessible. The black hole interior doesn't exist independently. It's a quantum error-correcting code that reconstructs information from the boundary. But this meant something terrifying. For most of the black hole's lifetime, the information is genuinely inaccessible, not just hidden, but in a state where asking "where is it?" has no meaningful answer.
Part B. Deeper implications. The interior doesn't exist. By 2020, physicists began confronting an unsettling conclusion. The interior of a black hole, the space between the event horizon and the singularity, might not be a real place. From the outside, you never see anything cross the horizon. Objects appear to freeze on the surface. From the inside, if you fall in, you experience crossing the horizon and reaching the singularity. But these two perspectives are complementary, not compatible. There's no single reality that includes both perspectives simultaneously. Physicist Leonard Susskind proposed black hole complementarity. The interior and exterior descriptions are both valid, but exist in different reference frames that can never be compared directly. An outside observer sees information encoded on the horizon. An infalling observer sees empty space and a singularity. Both are correct. Neither is more fundamental. This means the volume of space inside a black hole doesn't have objective existence. It's a perspective-dependent phenomenon, real for someone falling in, but not real for someone staying outside. Space itself is observer-dependent. The scrambling time. This led to calculations of how long it takes for information to become irrecoverable. The answer, the scrambling time, approximately the time light takes to cross the black hole, multiplied by the logarithm of the black hole's entropy. For a solar mass black hole, that's about 1 millisecond. What this means is horrifying. 1 millisecond after you cross the event horizon, the information about your quantum state has been so thoroughly scrambled into the black hole's structure that it's effectively destroyed. Not actually destroyed, it's still there in principle. But reconstructing it would require you to collect and analyze every single particle of Hawking radiation the black hole will ever emit over the next 10 to the 67 years, and perform a quantum computation more complex than simulating the entire universe. The information exists, but it's lost forever for all practical purposes. The entanglement structure. That's when researchers understood the true horror. In 2015, physicists proved that the smooth spacetime inside a black hole is generated by quantum entanglement between particles at the horizon. Cut certain entanglement links, and space itself tears apart. But Hawking radiation breaks these entanglement links. As the black hole evaporates, the entanglement structure maintaining the interior geometry is destroyed. From the perspective of someone inside, space is disintegrating around them, not because of the singularity, because the quantum entanglement creating space is being stripped away by radiation. You wouldn't fall into the singularity. You'd experience reality itself unraveling as the entanglement maintaining your existence dissipates into thermal radiation. The ultimate loss. That's when the full implication crystallized. Every piece of information that crosses an event horizon enters a state where it becomes exponentially more difficult to recover as time passes. After the scrambling time, effectively irretrievable. After the page time, requires collecting half the radiation. After evaporation, requires analyzing all radiation with quantum precision. In our universe, there are approximately 40 quintillion stellar mass black holes. In galactic centers, there are supermassive black holes containing billions of solar masses. Every second, countless particles, photons, and quantum states are crossing event horizons throughout the cosmos. All of that information, representing actual physical events, real histories, genuine facts about what happened, is being lost. Not destroyed in violation of quantum mechanics, but scrambled so thoroughly that recovering it requires resources exceeding what exists in the observable universe. The evidence no longer pointed to a phenomenon. It pointed to a flaw in our understanding of reality itself.
Act 3. The Big Picture. Part A. Theoretical Framework. The three interpretations of information loss. Today, three major frameworks attempt to explain what happens to information in black holes, and they paint very different pictures of reality. The holographic preservation model, championed by researchers like Leonard Susskind, maintains that information is never truly lost. It's encoded on the event horizon, then gradually transferred to Hawking radiation through quantum correlations. The information exists throughout the process, just in increasingly scrambled form. This model preserves unitarity and quantum mechanics, but at a cost. Spacetime isn't fundamental. It's an emergent phenomenon from quantum information. The interior of a black hole is a holographic projection that only exists relative to infalling observers. The soft hair model, proposed by Stephen Hawking in 2016, suggests that information is stored in soft hair, zero-energy quantum states at the event horizon. These states don't contribute to the black hole's mass or charge, but they encode information about what fell in. This model preserves general relativity's smoothness while allowing information escape. But it requires an infinite number of quantum states at the horizon, and nobody has proven these states can actually encode all the information. The remnant model, a more radical framework, proposes that black holes don't evaporate completely. When they get small enough, near the Planck mass, quantum gravity effects prevent further evaporation. What remains is a Planck-scale remnant containing all the information. This model preserves information by hiding it in microscopic objects, but it predicts an infinite number of possible remnant states, which creates its own paradoxes. Each interpretation resolves the paradox while creating new mysteries. This forces us to reconsider the most basic assumption of all, that information preservation is more fundamental than space-time geometry. The quantum gravity connection. But beyond these interpretations, the information paradox is really about quantum gravity, the still undiscovered theory unifying quantum mechanics and general relativity. Every attempt to resolve the paradox requires physics beyond the standard model and general relativity. String theory addresses it through holography and extra dimensions. Loop quantum gravity addresses it through discrete spacetime structure. Both approaches suggest that at the Planck scale, spacetime is quantized. It's not smooth and continuous, but granular, like pixels in an image. At this scale, the distinction between inside and outside the event horizon becomes meaningless. Information isn't lost because the interior doesn't exist as a separate region. It's a quantum superposition of states distributed across the horizon. The consciousness connection. Some researchers have explored an even more radical question. Does information loss affect consciousness? Your brain is an information processing system. Your memories, thoughts, personality, all information patterns. If you fell into a black hole,
From your perspective, you'd experience falling until hitting the singularity. But from the outside universe's perspective, you'd freeze at the horizon, your information becoming scrambled beyond recovery. Philosopher David Chalmers has discussed whether this creates a branching of consciousness. Does your subjective experience continue in the frame where you fall in, while simultaneously becoming scrambled information in the outside frame? Are these two versions of you both equally real? Or does consciousness require information to be accessible, meaning you effectively cease to exist when your information becomes irretrievably scrambled? There's no consensus, but it reveals something profound. Information isn't just about physics, it's about existence itself. If your information is lost, are you lost? Part B. Future Implications. The far future universe. Let's consider what information loss means for the universe's ultimate fate. Current cosmology predicts that in approximately 10 to the 100 years, all matter will have either fallen into black holes, been torn apart by cosmic expansion, decayed into photons and neutrinos. The black holes will then evaporate over timescales of 10 to the 67 to 10 to the 100 years. What remains is a cold, empty universe filled with thermal radiation, a featureless sea of nearly zero-energy photons. Every structure, every pattern, every bit of information that ever existed will have been processed through black holes and converted to thermal noise. The universe will have no memory of its own history. Not because information was destroyed, because it was so thoroughly scrambled that reconstructing anything meaningful would require computational resources that no longer exist. The universe will have effectively amnesia. This is the heat death, not just thermodynamic equilibrium, but informational erasure. The information rescue scenarios. Some physicists have proposed ways to preserve information against this fate. The Boltzmann brane hypothesis. In an infinite future, thermal fluctuations will randomly assemble ordered structures, including conscious observers. These Boltzmann branes would spontaneously form from the thermal bath, possess random false memories, and dissolve back into chaos. If the universe lasts forever, you're statistically more likely to be a Boltzmann brane with false memories than a real observer in a real universe. The vacuum decay rescue. If our vacuum isn't the true ground state, the universe might undergo vacuum decay, transitioning to a lower energy state. This would propagate at light speed, destroying everything in its path, but potentially creating new physics where information isn't lost.
The quantum resurrection. Some interpretations of quantum mechanics suggest that in an infinite multiverse, every possible configuration of information exists somewhere. If so, every state of information that ever existed continues to exist in some branch of the multiverse. Nothing is truly lost, because somewhere, in some branch, it still exists. None of these are proven, all are speculative, but they reflect deep unease about information loss. The measurement problem. The information paradox also connects to quantum measurement. When you measure a quantum system, the wave function collapses from superposition to a definite state. Where does the information about the other possibilities go? Standard quantum mechanics says the other possibilities simply cease to exist. Information about them is destroyed. But this violates unitarity, just like black holes do. The measurement problem and the black hole information problem might be the same problem. If consciousness causes wave function collapse and collapse destroys information, then every conscious observation is committing informational genocide, erasing entire branches of reality. You might be destroying information every time you look at something. The ultimate question. But even if we solve this mystery, it leads to a far more disturbing question. If information can be lost, even practically if not fundamentally, then the past is not permanent. Events that happened can become unknowable. History can be erased. Everything you've ever learned could be scrambled beyond recovery. Every memory you have exists only as long as the physical patterns encoding it remain intact. When your brain dies, when the atoms scatter, when they eventually fall into black holes and evaporate as thermal radiation, you will be lost. Not just dead, lost. The information pattern that was you scrambled so thoroughly that reassembling it would require reversing entropy across the entire universe. The you that existed will have been erased from reality. Act 4. The ultimate questions. When information becomes identity. There's a perspective shift that happens when you truly understand information loss. We typically think of ourselves as continuous beings, the same person from moment to moment, day to day, year to year. But what you really are is an information pattern. Your body replaces most of its atoms every few years. The matter composing you is temporary. What persists is the pattern, the specific arrangement and relationships. You are information, temporarily encoded in matter. And information can be lost. This means you're not permanent. You're not inevitable. You're a specific, fragile configuration that requires continuous maintenance. Stop maintaining the pattern and you cease to exist. Not your matter, that persists, scattered into atoms. But you, the information pattern, can be erased. The library analogy. Imagine the universe as a library containing every possible book, every arrangement of words, every story, every fact. For 13.8 billion years, the universe has been writing specific books, the history of stars, galaxies, life, consciousness. Black holes are fires burning through the library, not destroying the paper, the atoms persist, but destroying the information, the specific sequences, the meanings, the stories. After the fire, you have ash. Atoms still exist, but the books are gone. The universe is burning its own library, and unlike a human library where some copies survive, there's only one copy of each event. When that information is scrambled beyond recovery, it's gone from all of existence. The universe loses the record of its own history. The simulation hypothesis connection. This connects to the simulation hypothesis in an unexpected way. If we live in a simulation, information loss is just the simulator pruning unnecessary data. Events get compressed, then deleted when no longer needed for the simulation to run. From inside the simulation, this would look exactly like black hole information loss. The holographic principle would be evidence that reality is rendered on a lower dimensional computational substrate. Black holes would be garbage collectors, removing information that no longer serves the simulation's purpose. This isn't proof we're in a simulation, but it suggests that information theoretic principles might be more fundamental than physical laws. The universe might be computational at its core, with physical reality emerging from information processing, and black holes are the universe's delete function. The existential horror.
But let's confront the truly disturbing implication. Everything you know, everyone you've loved, every experience you've had, all of it exists only as information patterns. Those patterns are temporary. They persist only as long as they're maintained against entropy, and eventually they will fall into black holes or be dissipated by cosmic expansion. There's no cosmic backup, no universal archive, no way to retrieve lost information except to have recorded it before it was lost. And even recordings decay. Even the most durable storage will eventually fall into a black hole or be ripped apart by expansion. On a long enough timescale, everything is forgotten. The universe will lose its memory, and with it, any record that you existed. The question we cannot answer. And that brings us to the question this entire journey has been circling. We've discussed how information is scrambled in black holes, why quantum mechanics demands preservation, how resolution attempts create new paradoxes. But we haven't answered the deepest question of all. Does it matter? If information about the past becomes irrecoverable, does that make the past less real? If nobody will ever know about something that happened, does it still count as having happened? Philosophers call this the problem of past existence. Events in the past can't be observed directly. We infer them from present evidence. But if all evidence is destroyed, does the past event still exist in any meaningful sense? Two possible answers, neither comforting. Realism. The past is absolutely real, independent of evidence or memory. Events happened even if all record is lost. This preserves history, but makes it ultimately unknowable, a universe full of forgotten ghosts. Informationalism. The past exists only insofar as information about it persists in the present. This makes knowledge possible, but implies that the past literally ceases to exist when all information is lost. If informationalism is correct, then black holes don't just scramble information, they erase history. They delete the past from existence. Every event that crosses an event horizon becomes progressively less real as information about it is scrambled until it finally ceases to have existed at all. The universe isn't just forgetting its history, it's erasing it retroactively.
Now, concluding this journey within the black hole, we saw the transformation. Remember the question we started with. What happens to information that falls into a black hole? We've traced how that question revealed the deepest crisis in modern physics, a conflict between our two most fundamental theories. We've seen how black holes appear to destroy information, violating quantum mechanics. Holography suggests information is preserved on event horizons. The information paradox forces us to question the nature of spacetime. Practical information loss makes the past progressively unknowable. We now know that asking, is information preserved or destroyed, misses the point. Information is preserved in principle, but lost in practice. It exists, but becomes irretrievable. The past remains real, but becomes unknowable. But the mystery isn't solved. If anything, it's deepened. We don't know if black holes truly destroy information or just hide it perfectly. We don't know if the interior of a black hole is real or a perspective-dependent illusion. We don't know what happens at the singularity where all our physics breaks down. We don't know if there's a way to rescue information from black holes using technology we haven't imagined. The ongoing journey. Right now, as you process these words, information about this moment is being encoded in your brain's neural patterns. Those patterns will persist for hours, days, maybe decades. But eventually, the information will degrade, be forgotten,
be lost to entropy. And across the universe, black holes are processing information through their event horizons, scrambling it into thermal radiation, erasing the detailed history of what fell in. Stars, planets, entire civilizations might have fallen into black holes, their information lost forever. In the coming years, new observations of black holes will test information preservation theories. Gravitational wave detectors might observe information-carrying signals in black hole mergers. Quantum gravity theories might reveal new mechanisms for information escape. And somewhere, right now, a physicist is scribbling equations that might finally resolve the paradox or deepen it into something even more disturbing. The universe does not owe us permanence. It does not guarantee that what happens will be remembered. Information loss is not a flaw in physics, it's a feature of reality, a reminder that everything is temporary, including knowledge itself. You are an information pattern witnessing information patterns being destroyed. You are the universe observing its own amnesia. You are knowledge contemplating the inevitable loss of all knowledge. Every moment exists only once. Every experience is unrepeatable. Every piece of information you preserve is fighting entropy. The universe is forgetting. But for now, right now, in this moment, you remember. And that might be the only permanence we ever get. If you liked this video and found this concept interesting, please do share your thoughts and kindly like and subscribe the video. It would really help me, Akash, the one behind the Cosmic Ledger. I work really hard for these videos, like really, really hard, so I would really appreciate your support.